Well, good morning, everyone. Let's begin. The project area selection handout that I gave you last Tuesday when we met, I'm going to look over what you've got so far when you're working on something else today. But I'll ask you to actually submit that on Thursday. So if you still haven't made all the progress that you need, you've still got a bit of time. I'll take that at the beginning of class on Tuesday. Next week, class is going to be online, and I've posted online a single continuous software demo. And the recording is only 23 minutes long, but it'll take you maybe 2 hours, possibly more, to actually get through the demo, because what you're going to need to do is pause as the computer does certain things. I mean, as I was preparing the demo, I would pause it as it was downloading some data, and most likely I can jump through the hoops on the computer a little bit more quickly than you can, since you haven't used the software before. So don't be deceived by the fact that the recording is only 20-something minutes long. It'll probably take a while for you to get through. So what I'm going to give you is a spot on MU Online where I'd like you to post an Excel file to MU Online to show that you've gone through that demo. I just would basically like you to mimic the exact same things in the exact same location that I do in that online demo. And the reason why is it's introducing a concept that's called stochastic modeling that we won't have a chance to get to this week, but it really expands the power of the software. So that's what we'll be doing next week, and I'll remind you again on Thursday about that. And homework 11, which I'll distribute to you today, is for the Watershed modeling system that we're going to be learning today and on Thursday, and it'll be due on Tuesday, November 18th, and that'll be the first class meeting when we get back together in person. So the class is going to be very different from here till the next couple of weeks because of the emphasis on the software. We're trying to get you more application-oriented and being able to solve problems and do projects, and so it won't be quite as much lecture as there has been previously. Any questions related to the announcements or scheduling of the course for the next couple of weeks? All right. So, like I mentioned, I wanted to look over your project area selection. Please set that on the table next to you, and what I'm going to have you do, I forgot to bring in some scissors. I'll go to my office and grab some scissors. I've got a handout here that has a bunch of boxes on them. And in each of the boxes is some words that's related to a concept from the course so far. So, for example, one of the boxes says abstractions and infiltration. One of the boxes says rainfall excess. One of them says curve number. So what I'd like you to do is cut out all these boxes and start arranging them on the table in front of you. You may need to put some things underneath the table so you've got space to work. But this is something I do each semester to try and get students to think about what's the big picture of the course. Like, what kind of information do you have as a hydrologist, and what does it lead to? We've talked about this before, but this has a lot more pieces than the usual thing that I draw on the whiteboard when I'm telling you how hydrology and hydraulics interact with each other. So I'd like you to use as many of these boxes as possible. Some of them maybe would just be off to the side and like tangentially related to some of the main concepts, and in a couple of cases there's a blank box where you could write a concept that you think is missing. So the whole point of this exercise is for you to be thinking about what is watershed modeling, because that's what we're going to be doing with the computer, and I don't want us to jump into what the computer is simulating before you've had a chance to think about the big picture. So let me hand this out, and I don't have 23 sets of scissors. I think you're going to have to share scissors or maybe just start ripping these out by hand. But we'll have about 20 minutes or so before I ask you to get with a partner and explain the model that you have put together of the conceptual model. The conceptual model is just, what kind of work are you doing and how did the pieces fit together? It's okay if you want to chat as you're doing this, but I do want each person to have their own conceptual model, and then there'll be time for a little bit more collaboration in just a minute. So So basically, in the hydrology part of it, which is what we're focusing right now, what is the flow rate? So some of the things that you need to characterize in order to find out what's the flow rate is, of course, land use. So that's one of the boxes, soil type. And you've learned recently that those two things come into curve number. Remember, curve number is a kind of a quantitative representation of how much infiltration there will be versus how much runoff there will be. And you learned recently that once you have the curve number, then that leads you to calculating S, which is the storage. And so the thing that I wanted to try and piece together is what's the relationship between some of these concepts. And this is just an example of how land use, soil type goes to curve number goes to S, storage. And once you know the storage, then you can have a runoff model. So let's see, what sort of options have I got here? You can use that to calculate the S plus precipitation. So you have a few boxes that talk about precipitation. S and precipitation both go together for you to calculate the rainfall excess. And once you know the depth of the rainfall excess, then that can lead you to a hydrograph. And so you know the picture that you've got of a hydrograph. So I think there's also somewhere it says SCS dimensionless unit hydrograph. And so that would be another thing that along the way, SCS dimensionless unit hydrograph. So that is what's used to come between the rainfall excess depth and the actual runoff hydrograph. How do some of these other things fit in here? The average basin slope would go into knowing the time of concentration, and you'd use that in the dimensionless unit hydrograph. Clay soils don't drain very well. That's going to go into like an adjacent concept to soil type. So basically, it's just thinking about what's the workflow that you have in trying to analyze what's the hydrograph at the very end. And some of the information is extraneous, and you'll always have so much extraneous information when you're an engineer running an analysis. There will be a lot of things that just simply don't apply, or some things that are related but are not deterministic. So for example, clay soils don't drain very well. You know that information, but it might be that only part of your watershed is clay soils, that calculating the curve number is sort of a composite. So you have to be aware of some concepts, and maybe it'll influence where things are going, but not be strictly like the only thing that yields a certain curve number, for example. All right, so I hope that sort of got the mental juices flowing for what we're going to do with the rest of class today. I'm going to give you a very brief software demonstration with WMS, and I don't expect you to follow along with like the clicks that I'm going to be doing. I just want to introduce you to what the program looks like and what it does, and then in class on Thursday we're actually going to do the thing where I say, okay, now click here, zoom in on this thing, all of that sort of ideas. By the way, if you've got your tiles organized in some sort of a conceptual fashion, like I mentioned, I'd like you to take a picture with your camera phone just so you've got reference to that later. If you already scrambled them up and didn't take a picture, that's okay, but if you do have some sort of an order there, I'd like you to take a picture of it. All right, so I'm going to show you a few things about WMS today. Did that. The purpose of watershed modeling, like WMS, is to be able to rapidly and repeatably predict what the runoff is going to be for a certain area. And defensibility is something that's really important to hydrologists, and it's because there's a lot of wiggle room in the analysis of how much runoff there's going to be. Some things are subjective, like you already know that a C value can be very subjective. When you're using the rational method, sometimes it's hard to know for A grassy area should use a C value of 0.4, a C value of 0.5. And so think about a legal case where the Division of Highways had a culvert and it was too small. And so now they're getting sued. It damaged someone's property. There was problematic flooding. And so what a hydrologist has to be able to do when responding to the questions from lawyers is show that what they did was consistent, reliable, justifiable, quantitative. You don't want to sit on the stand in a legal case and they say, why did you make the culvert 18 inches? And you say, I just felt like it. Or it seemed like a good idea. You have to have a process and some sort of a standardized way to come to answers. And programs like WMS are very effective at creating a standardized way to say, this is the procedure we're going to follow, even though some parts of it are subject to interpretation. The process is reliable and consistent. Here's the WMS, and this is version 9.1.12. If you go to About, all of you who've installed it on your computer, since this was built in May 2nd, if you've installed it this semester, it's going to be the same 9.1.12. The version that's installed on the tablet PCs might be a little bit older than that. And depending on how old, we might update it, and maybe we won't, because in a lot of cases, they're just fixing minor bugs that won't affect us at all. But in some cases, it's a pretty important update. So we'll just have to play that by ear and see how many students are using the tablets instead of installing it on your own computer. All right, so right here is a list of tools that changes depending on what module you're in. And as I click through different modules, you'll notice that these are the main modules here. And down at the bottom of the screen here, it tells you what the cursor is hovering over. So if you don't know the name of a tool, or if you think that one of these is going to do what you need, if you wait for a second, the name will come up, and then at the bottom here, it tells you what to do with it. So for example, sometimes you'll be reading through a tutorial and it'll tell you to go to the drainage module. If you don't remember which of these is the drainage module, you just have to hover your cursor over it for a little while and it'll come to there. What's nice is that in recent years they created a wizard that it steps you through the whole process automatically. When I learned WMS, when I was an undergraduate student a long time ago, I just basically had to memorize what the workflow was. But now, once you click the hydrologic modeling wizard, then it tells you, first, do this, step A. So I'll click it right here, and it tells you the first thing you need to do is save a project file name. So if you just browse to some location that you're going to be able to find later, like in your My Documents folder. In this case, I'm just going to put it in a temporary folder here. I'm going to call it 433 Demo. And you have to click Save here. It actually hasn't saved anything. If you notice up here, it still says it's untitled. But if I click Save, then it creates a .wms file. I'm going to mention this because it's really important that it creates a lot of different files besides just that WMS file in the process of watershed modeling. So you'll see here there's a .sto file right now. There's going to be several others along the way as I download elevation data, land use data. So maybe I actually better put it in its own subfolder here. So let me create a new folder. I'm going to call it 433 WMS Demo. I'm going to save this file in there so you can see all of the things that it downloads along the way. Save. All right. So here next, then it tells you the next thing to do. And as you might expect, what you have to do is define a project area. In one of the activities that I'm going to ask you to do for class next week, where you're doing the stochastic modeling, I give you the coordinates, so you can just type those in. That's not the normal thing. Normally, you don't know the coordinates of your project area. You just know what it looks like because you browsed to the project area on Google Earth. And so what you have to do, you click on this Define Boundary button, and then you start browsing around. Now, maybe a few of you have taken a GIS class before, but this projection here where it's saying UTM, NAD 83, meters, there's different coordinate systems, and For example, when you use GPS, you're probably already familiar with latitude and longitude, you know, like 82 degrees north, 43 degrees west, and that sort of thing. UTM is called Universal Transmercator, and it's a different way of keeping track of coordinates. It's not latitude and longitude. Hopefully that'll be the default thing that comes up when you start your modeling, but if it's not, you need to put it on this. And we are here in West Virginia. We're in Zone 17, and that's an important thing also, is different parts of the United States are in different zones, but all of West Virginia is in Zone 17. And so you can change it if it comes up as latitude, longitude, then you'll want to change it to UTM and then change it to Zone 17. NAD 83 is just talking about like what they use as the starting point for all of these coordinate systems, and that was just, it was a survey that was done in 1983, and it's best to leave the units in meters because that's most of the elevation data is going to come to us in meters. So that was the default when I started up, but that shows you how you can change it into the projection that you need. So Define will bring up like a viewer tool where you can start browsing around the area. So if I'm interested in this watershed out where I live, you know, I live in Ona, which is a little bit further away. Here's Huntington, so I can go over here to Ona. Some of you picked watersheds in like Pocahontas County, so what you'll need to do is zoom out on the map of Google Earth and see, okay, well, my watershed is halfway between Gladeview and Buchanan. So then you just zoom in, scrolling, zooming in, and you'd say, okay, my watershed is in here. And it doesn't have, don't zoom in so that it only includes your watershed. Get a little bit of a buffer around the edges, because if you accidentally cut off your watershed, then you have to download all of the data over again. So you want to make sure that definitely the watershed you're modeling is contained within the area. But you don't want it to be too big. Like if you said, this is my project area, then it's going to take literally hours to download all of the elevation, soil, land use. So you want to find a happy medium where you know that your watershed is in the bounds that are shown on the screen here, but you don't want to be getting enormous areas because you can crash the program and it's just a waste of time. So let me go back over to Ona, so between Huntington and Charleston, zooming in, all right. So the watershed I'm interested in is inside of this area, so I'm going to click OK. Now that thing, my wizard went away, and this is kind of a funny little bug, is sometimes it does that, like it vanishes all of a sudden. All you have to do is click on this again, down and back up, and then it reappears. I don't know why it does that, but it's somehow like this gets stuck in the background when you finish up defining the project boundary. You'll see that it filled in these coordinate values. That's basically just the edges of the area that I'm viewing. So if I go back to here, that's looking at the left corner, the lower left, the upper right, the lower right, and those coordinates, whatever's on the screen there, it's going to use as the project boundary. So this is the great thing about the program, is that it's going to go get all the data that we need for watershed modeling. We don't have to download it separately, like even just a year ago, 2 years ago, you had to go to some other website to get the soil data, another website to get the land use, but basically it automatically goes to those websites and gets the data that you need now. So this use web services allows it to connect to the internet and find the information that you're going to need. And we're going to get 3 different data sets. We're going to get, I'll scroll over here, we want it to get the elevation, the land cover, and the soil type. And the soil that we want is Surgo. Surgo is like high resolution soil data. StatsGo is kind of low resolution soil data. And I think I've got that right. They're so similar in name that I sometimes mix them up, but it's the Surgo that I think is the high resolution. Okay, you'll notice that there's a couple of different elevation options, or resolution options for the elevation data, 10 meter, 30 meter. And what that's talking about is how far away the spaces are. It basically is going to break my watershed up into a grid, and at intervals identify the elevation here, 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 and so 10 meters means that it's 10 meters between elevation measurements. So if you have a small watershed, like only 10 acres or so, then it's critical for you to get the 10-meter resolution, because you want to have as many of those elevation points in your watershed as you can. And in fact, West Virginia is one of just a handful of places that has even better than 10-meter resolution. They have 3-meter resolution, but that you do have to go download separately. If you're working with a really small watershed, then I encourage you to come see me and I'll show you how to get the super high resolution elevation data. But for most of us, the 10-meter will be fine. If you're working with a large watershed that's maybe 10 miles or bigger, then you might want to switch to the 30-meter resolution just because it takes less time to process. But I'm going to go ahead and get the 10-meter elevation data, land cover, and soil type. There's other things that you can have it open, like images and topo maps, but I'm not going to get those now. I can just add them later if I need them. So I click on this button and it automatically starts connecting to those websites that have the data. And it's asking me the cell size for the elevation data. And so it sometimes will like resize it so that it's not too big. If you're downloading the data, and you can never make a mistake if you just click OK. But like if it had offered this window and said something like 14.7, what it's saying is, do you want me to download all of the data and use that in high resolution mode, or do you want me to downsample a little bit, like resize it so that it's easier to use? Ultimately, it doesn't really matter. I usually, if it told me 14.7 and that's what it was offering, I'd override it and I'd say, no, get all the data, get the 10-meter resolution instead of like resampling it. But it won't give you mistakes if you... Now, it's asking the 30-meter about the... I think the land cover is at 30-meter intervals. And so it's just asking, do you want me to resample it? Like if I wanted, I could say 100 meters, and then it would take up less memory once I save it. But just click the defaults. That's okay. So it's got the elevation and the land use. Now it's getting the soil data. And that generally takes the longest because it's really bad about picking only the area that I need. Did you have a question? You'd usually look at topographic maps, like that's put out by the Forest Service or somebody like that. All right, so over here it's telling me all of the data that it's downloaded, and then it's going to continue to take me through this wizard. I can close the wizard at any time and come back to it. So I want to start looking at my data, so I'm going to close the wizard, but that's not like I can never come back. If I want the wizard again, I can just click on that button and then come here, and I just finish this, and so now it's offering me to show me what's next in the steps. But looks like it didn't get the land use data, or at least it's not turned on. Let's see. Soil. Oh, okay, yeah, there's the land use. It wasn't switched on, but it's there. So let me zoom to here. This is the elevation data, where red is a low point, green is a high point. Here is soil data. So if you can see that the land use and here's the land use. If I turn that on, all the data I'm going to need to calculate curve number is there, but it also downloaded some data that I don't need. Like if I zoom out to the entire extent, for some reason it got all this soil data in Ohio. Like all of this soil data, I don't need it because I already defined my project area is in here. So I'm just going to tell it to delete this extra soil data here. If you right click and you can delete what we don't need. All right. So I'm going to work with the elevation data. The next thing that you do in the like the workflow is something that's called Topaz. And that's an interesting thing. What it does is, remember that the elevation data is all of these points that says what the elevation is. And so Topaz looks at, it calculates an elevation for an area. So maybe this elevation is 10 meters, this is 9, this is 9, this is 8. What Topaz does is it looks at all of the adjacent cells, and it finds out what direction the water is going to flow. So if it's looking at this cell, it's going to look at everything surrounding it, and it wants to know where's the lowest place. And so it would say all of the water that falls on this cell is going to go into this one. And then for this one, it's going to say all of the water from this cell is going to go, and then it looks at the surrounding ones, and it finds what has the lowest elevation. So for every single one of the pixels that's in here, it's going to try and find out what's the lowest point. Let me see. It's been a while since I turned on the pixel view of elevation, but there is a way to do it. The DEM data, yeah, here's the points. Actually show all of the data points themselves. Zoom in on a little spot so you can see how many of them there are. So every one of these points, it knows the elevation at that point. And this thing Topaz is it's going to look at every single one of these points and try and find out if a raindrop falls there, what direction is it going to travel. So it's a pretty CPU intensive process, but it's amazing how quickly it actually goes. Let me turn off those points, and then I'm going to run Topaz. And so, like, how do you remember to run Topaz? Well, you just go back to the wizard, and we already downloaded the data. We don't need to read the data because we downloaded it, but we're going to compute Topaz. You click that button, and it's already finished. Normal program termination. And it's going to add something. It's going to add its best guess of where the streams are based on that. And you'll notice that it's putting the streams at the low point of the elevation data. And that makes sense. It's basically saying how much area is upstream of a certain cell, and then it's assuming that when it rains there will be water there. And we can change that. Like here you can say, I want it to assume that there's a river if there's 0.05 miles upstream of that. But let me zoom out a little bit and watch what it does when I change that assumption. Okay, so here in the display data it was 0.05. What if it's 0.02? It's going to show a lot more streams because it requires less upstream area. So I click OK, and now you'll notice that there's all these additional branching streams. So basically it's just a way of visualizing where the data is. Now there's one last thing I'm going to show you today, and that's adding the outlet. So if you have an image and there may be a road that goes along this stream, and so here at this location would be maybe a spot that I'm interested in knowing what's the flow rate because maybe there's a culvert here. So this outlet point, if I just drop an outlet on top of the stream, then I can have the computer automatically find out how much area is upstream of that outlet. So what you have to do when you're using Google Earth is just sort of manually draw a line along the ridgeline and guess that this is the watershed. But what the computer can do, you just say delineate basins wizard and then delineate watershed, and it automatically calculates here is the area that is contributing to the outlet at that point. You can see it calculated 0.26 miles, or if I want to see that in terms of acres, I just change the units here from square miles to acres, okay, and have it do that calculations again, delineate basin, delineate watershed, okay. Now it'll express it 167.39 acres. So it's really accurate. It's able to follow the ridgeline with a lot more precision and patience than we would if we were tracing it manually. Okay, so when we get together on Thursday, we're actually going to dig in. I encourage you to download and install the program on your computer before Thursday, and also remember that you're going to need to submit that project area selection document to me on Thursday. Please clean up all the little bits of paper. It was a messy class period. Please just jam it in the garbage there so that the students themselves in the next class don't have to deal with it. I'll see you on Thursday.